today's lesson, we are going to talk about implicit differentiation. In order to talk about that, we need to talk a little bit more about what we mean by implicit. An implicit equation is one in which x and y are not functions in terms of the other variable. Okay, what we mean by that is normally we talk about y being a function of x, so y can be written as f of x equals some expression. If I'm talking about an implicit equation, here's an example of one, x squared plus y squared equals 4. In this case, the circle is what we'd consider an implicit equation because if I try to solve for x, I can get it in terms of y, or I can solve for y in terms of x. But notice neither of these are functions, and that's mostly because of the plus or minus. In other words, they'd fail the vertical line test. Okay. Another way to see this is kind of pictorially. If I actually look at the graph, this is a circle of radius 2, and I can see that if I try to use a vertical line anywhere, it's going to hit in more than one spot. And likewise, if I try to use a horizontal line, so if I'm thinking x as a function of y, if I pick any horizontal line, I can see also that it's going to hit in more than one spot. So by an implicit equation, it just means I can't rewrite the equation in terms of one variable and make it a function. Okay. And the reason we're going to look at implicit differentiation is because even though this isn't a function in terms of either variable, circles and ellipses and things like this that are implicit equations are nice things we want to work with. And they're still going to have slopes and tangent lines, just like things we've looked at before. Okay. So, to find the derivative of an implicit equation, basically what this means is I want to find dy dx, so our derivative. We're going to treat x as the variable, since that's the one on the bottom, and y is going to be a function of x. In other words, we're going to think of it as y of x. So in this case, y of x is some equation that's in terms of x. We just don't know what that equation is. Okay? So let's use that circle as our example. X squared plus y squared equals 4. Okay? So here, we're going to take the derivative of each term, treating y as a function of x, and to do that we're going to use the chain rule to take that derivative. So here, x squared, I can think the derivative there is just 2x. The derivative of y squared, so again if I'm thinking of it as y of x, it's going to be 2y times the derivative of y with respect to x. Now again, we don't know what that is, so we can't actually put an expression there other than derivative of y with respect to x. And then on the other side of the equal sign, our derivative is just 0. Okay. Now that we've taken the derivative everywhere, we want to isolate the dy dx term. Okay. So now I'm basically solving an equation. I want to solve for this dy dx. So 2y dy dx will equal a negative 2x, and then I'm just going to divide out. So dy dx is going to equal negative 2x over 2y. Okay. And last, just like any other equation, we want to simplify what's left over. Now, not all of them are going to look quite this nice, but here in this case, if I simplify, we can see dy dx is just negative x over y. There are two things to notice in this derivative. Again, the first is that implicit chain rule. And I say implicit because it's not looking like a chain rule. I'm basically just taking a derivative like it normally had, but again, you have to remember that y is being treated as a function of x. And then the other thing to notice is once I get that derivative, notice it involves both variables. So not only is it a function of x, but it also has y's in there. So our dy dx is also an implicit equation. Okay. So let's look at another example. Let's take x squared plus 2xy minus 3y squared equal to 1, and let's find its derivative. Okay. So again, the first thing we're going to do is take the derivative of each term, treating y as a chain rule. Okay. Now the difference between this one and the last equation is, we'll notice once we get to the second term, the 2xy, I have to treat this like a product, because now I have 2x, but then y is also some unknown function of x. So my derivative there is going to require my product rule. So I'll take the derivative of the first term, which is just 2, times the second, plus the first term times the derivative of the second. 3y squared, again, we'll treat normally first. So bringing the 2 down, we'll get a 6y times our dy dx, and that's going to equal 0. Okay. Again, next we want to isolate the dy dx. Now in this example again, I've got more than one dy dx term. So I'm going to get all the dy dx terms on one side. And everything else on the other side. Okay. I'm going to factor out the dy dx so that we can solve for that term. Okay. So dy dx will equal negative 2x minus 2y over 2x minus 6y. Okay. So now that we've isolated, we go back to the last step, which is to simplify the expression. So in this case, we notice that there are 2's in every term. So we can factor out a 2, cancel top and bottom. So there would be our derivative. So let's look at a couple more examples of implicit differentiation. Now for these, again, we're using some of the same basic properties that we used before. So we can see things like in the last example with the product rule, but we could also have quotient, chain, and power rules. Okay. In this example, here's one that involves our exponential functions. So x e to the y plus y equaling 13. We want to find dy dx. Okay. So again, the first thing to notice is the x times the e to the y again gives me a product rule. Okay. So taking my derivative here, derivative of the first term is just 1 times the second term plus the first term times the derivative of the second. Again, the e to the y, we have to use a chain rule. So that says it's going to be e to the y times the derivative of the exponent, which again is just going to be dy dx, plus derivative of y, which again is dy dx, equaling our derivative on the other side, which is just 0. Okay. Again, we want to isolate dy dx, so we're going to get those like terms together, everything else to the other side. From here, now we can factor out the dy dx. And isolate the dy dx term. In this case, there's not much more we can do to simplify that, so there is our derivative. Okay. So let's look at another example. In this example, the natural log of xy plus x is equal to 4. Same thing, we'd like to find dy dx. Okay. Now this one involves a chain rule in terms of the natural logarithm. So just like the last one, we had a chain rule in terms of the exponential. Here, we can see natural log of xy. We'll do the natural log first, and then worry about the argument. So our derivative there is going to be 1 over xy times the derivative of xy. xy, again, is a product. So here again, use my product rule. So derivative of the first times the second, plus the first times the derivative of the second. Our derivative of x is just 1, and derivative of 4 is 0. Okay. From there, again, we want to get our dy dx by itself. So, notice here this 1 over xy is being multiplied by everything inside the parentheses. So the first thing we're going to want to do is distribute. So 1 over xy times y looks like a 1 over x. 1 over xy times x dy dx looks like a 1 over y dy dx plus 1 equaling 0. Now we can move things around. So I can move the other terms to the other side. And divide out by my 1 over y. Okay. Again, always simplify, so we're not quite done. In this case, I've got some complex fractions in here, so I need to go ahead and simplify those. Okay. The thing to notice here is if I look at all the terms, my LCD is basically xy, so I can multiply top and bottom by that. So dy dx will look like a negative xy minus y all over x. And there, even though I can factor a y out of the top, there's not a whole lot more I can do with that. So there is my solution. Okay. In this next example, we have combinations of our exponential and our natural log. So we've got e to the x plus y equaling the natural log of x plus y. Okay. Again, for the e, I can think chain rule because again I have something other than x there. So the derivative is going to be e to the x plus y times the derivative of x plus y. In this case, it's not a product rule anymore because I have that plus sign in there. So the derivative of x plus the derivative of y for the other side, natural log of x plus y. Again, our natural log we know is 1 over the argument times the derivative of the argument. So in this case, times the derivative of x plus y, which is going to be the same as what we just did on the other side. From there, we need to isolate the dy dx's. So looking at our expressions, again, we've got some grouping symbols, so we need to distribute before we can get the dy dx by itself. So we'll have an e to the x plus y plus e to the x plus y dy dx. So distributing through here. Same thing over here, we'll get a 1 over x plus y plus 1 over x plus y dy dx. Okay, getting our dy dx terms to one side. And everything else to the other side. Same as last time, we'll factor out that dy dx. and divide out. Now again, at this point we would simplify, but one of the things to notice here is I have exactly the same terms, they just have different signs on them. So these actually cancel out. If I factor a negative 1 out of the top, I would see I get e to the x plus y minus 1 over x plus y. So here, this tells me that dy dx is just going to equal negative 1. One last example for implicit differentiation. So some of our applications that we've had up till now have just been finding the slope and finding the tangent line. We've also looked at some marginals, but I want to go back to the tangent line. So here's an example of implicit differentiation with that application. We want to find the slope of the curve, x cubed equaling y minus x squared squared, at the point 1, 2. And once we have that slope, we want to use that to find the equation of the tangent line. Okay. So again, to get the slope, I need to find the derivative. So first, I need to find dy dx. Okay. So just like what we've done in the last few examples, I'm going to take this implicit equation and take the derivative implicitly. So our derivative of x cubed is going to be 3x squared. On the other side, the y minus x squared squared, that's a power or a chain rule. So we'll bring the power down front, leave the inside alone, times the derivative of the inside. Derivative of y, again, is just dy dx, minus derivative of x squared, which is 2x. Okay. Now we just need to isolate the dy dx. Okay. Now, unlike the last few examples, notice this one I'm probably not going to distribute. I've got several sets of parentheses, and I've only got the one dy dx. So here I can actually divide out first. And then add my 2x. So there's the equation for my slope. Okay. So now that I've found dy dx, I need to find the slope at the point 1, 2. Okay. Now notice here, unlike the previous tangent lines and slopes that we did, those we only needed the x value in order to find the slope. In this case, because it's an implicit equation, I have to have both y and x. So if you're only given the x value, you're going to need to go back and actually find that y value before you can find the slope. Okay. So here, again, we know that dy dx is 3x squared over 2y minus x squared plus 2x. So our slope, in other words, dy dx at the point 1, 2, is going to be 3 times 1 squared, 2 minus 1 squared, plus 2 times 1. Okay. So we just plug in 1 for x and 2 for y. Okay. From there, we'll go ahead and simplify. So on the top, it looks like just 3. On the bottom, we get a 2 minus 1 times 2, plus our 2. So 3/2 plus 2 looks like 7/2. So there is our dy dx at the point 1, 2. Okay, so there's the answer to the first part of the problem, which was just find the slope of the curve. Now, to do the last part of the problem, we want to find the equation of the tangent line. Okay, so for part 3, find the tangent line. Okay, so here, to find an equation of a line, in this case, in particular the tangent line, I always need two things. I need the slope and I need the point. So here we know our slope, so dy dx at the point 1, 2 is going to be 7/2, and we know our point is 1, 2. So using our point slope form, this is an equation you definitely want to know. Again, anytime I'm using a tangent line, I need this form. So plugging in y minus my y1, my slope, x minus my x1. Okay. For equations, always put them in the slope-intercept form unless otherwise stated. So here we're going to go ahead and simplify this. So just distributing on the right-hand side. Now we're going to go ahead and add the 2. And there is our equation of our tangent.